A rocket can use 3 tons of fuel per second. And all this just to start. But how does it go up? And why doesn't it fall back down? Today, you will discover all of this. A rocket is basically a giant tube filled with controlled explosions, built with extreme precision. But not just any explosion. It carries 2 key ingredients that, when mixed, unleash a massive amount of energy. Fuel oxidizer, usually liquid. Oxygen. That's what fire needs to exist. Something to burn and something to feed the burn. The difference is, a rocket brings its own oxygen because in space, there's no air at all. Not even a little. Now picture this. You ignite that mix. It burns fast, extremely fast, and the reaction creates a constant explosion. But instead of exploding in all directions, the rocket's engine channels all that force in one direction, downward. And that's the secret. A rocket goes up because it throws mass down. That's how it moves. This is Newton's third law in action. For every action, there is an equal and opposite reaction. The rocket throws burning gas out the back and shoots upward. That's it. Think of it like a balloon with air rushing out. Except this one is designed to aim perfectly and never stops pushing. And here's another thing. A rocket doesn't need air to work. It's not like a jet engine. It can fire in a total vacuum because it doesn't push against air. It pushes against itself by throwing mass in the opposite direction. So for a rocket to work, it needs powerful fuel oxygen. Onboard, an engine. That can handle the pressure and a clear direction. In the end, a rocket is a cannon that never stops firing, aimed at the sky. It's a controlled explosion, with one purpose only: to escape Earth. Gravity is pulling on everything all the time. You, your phone, a missile, a spaceship. If something goes up and stops being pushed, it falls. Always. So escaping Earth isn't just about going up. You need to go up so fast that gravity can't pull you back down. That speed has a name: escape velocity. To break free from Earth, a rocket needs to hit at least 11.2 thousand kilometers per hour. That's over 9 times faster than a rifle bullet. If you launched at that speed, with no air to slow you down, you'd never come back. But a rocket doesn't launch like a bullet. It builds speed gradually, burning fuel while getting lighter every second. And there's another problem: air resistance. The atmosphere is thick near the surface. Going too fast too soon would heat everything up like crazy. So the rocket has to strike a balance. Go fast enough to fight gravity, but not so fast that it melts in the air. That's why rockets start by going almost straight up, to punch through the thickest part of the atmosphere. Then, slowly, the rocket begins to tilt, because going up isn't enough. To stay in space, it needs to go sideways, and fast. If it just goes up, it falls back down. To stay in orbit, it must reach an insane horizontal velocity, circling Earth, not just escaping it. Most modern rockets reach nearly 28,000 kilometers per hour sideways just to keep a spacecraft in stable orbit. In other words, a rocket doesn't just need to rise, it needs to run sideways so fast that Earth literally curves away beneath it. And that's why rockets need so much speed, so much fuel, and so many precise calculations. As soon as a rocket lifts off, it begins a kind of engineering choreography, and nothing about it is random. One thing most people don't realize is that the giant rocket you see standing on the launch pad doesn't make it to space in one piece. It's built in stages, separate sections that get discarded one by one as the rocket climbs. Think of it like peeling layers off an onion, and there's a very simple reason for that: weight. In space, every gram matters. If you try to carry everything all the way to orbit, you'll never have enough thrust or fuel. So the only option is to drop what you no longer need. Right at the start, the first stage kicks in. This is the most powerful, the heaviest, and the most fuel-loaded part of the rocket. Its one job is to blast off from the ground, punch through the thickest part of Earth's atmosphere, and fight against the crushing pull of gravity. While it's working, the whole rocket shakes and roars. It's the most intense part of the launch. But once the fuel runs out and that job is done, this massive section simply detaches and falls back to Earth, usually into the ocean. Depending on the mission, it might even be recovered and reused, like what SpaceX does with its boosters. From there, the second stage takes over. It's smaller, lighter, and much more efficient. By now, the rocket is flying high, above most of the atmosphere. With less air to push against, the engines can burn more cleanly and accelerate more precisely. The second stage pushes the payload further and faster, aiming to reach a very specific orbit. On more complex missions, there can even be a third stage, or a final boost module, used to fine-tune the trajectory or send satellites into geosynchronous orbits, much higher and more stable. This entire process, breaking the rocket into stages, is what makes spaceflight possible. A rocket is essentially a stack of controlled explosions that get thrown away one by one as they complete their job. That's how the mission stays light enough to reach orbit, without wasting fuel, on carrying dead weight. At the very top of the rocket sits the most important part of the entire mission, the payload. Compared to the rest, it might look small. But it's the whole reason the rocket exists in the first place. It could be a communications satellite, a space telescope, a capsule carrying astronauts, a robotic probe heading to Mars, or even a fuel module for a space station. This payload is protected inside a structure called the fairing, which shields it from air resistance, intense heat, and small debris during the climb. Once the rocket is out of the atmosphere, the fairing is no longer needed, and it's released. 2. The final stage burns a little longer, makes the last course corrections, and then separates. The rocket, once a towering structure made of hundreds of tons of metal and fuel, is now fully dismantled. What remains is a small, silent object, traveling alone through space at high speed, locked onto a precise path. And all of this, the launch, the staging, the separation, happens in just a few minutes. In less than 10 minutes, what was once a 50-meter-high beast becomes a tiny module orbiting the Earth at nearly 28,000 kilometers per hour. It begins as a fire-breathing monster on the ground, and ends as a quiet dot gliding through space, unseen, but doing exactly what it was, built for, delivering something to orbit with absolute precision. In space, there are no roads, no up or down, no left or right. So, how does a rocket know where to go? Or even how to turn? The answer is maneuvering thrusters. Tiny nozzles placed around the spacecraft that shoot out little bursts of gas. And in space, that's all it takes. If the rocket fires gas to the left, it turns to the right. Fire downward, it tilts upward. It's simple physics, action and reaction. These thrusters are scattered across the capsule or satellite, and they're controlled by onboard computers with insane precision. Want to align with the space station? The thrusters gently rotate the rocket until it's locked into position. Need to release a satellite? They fine-tune the angle down to fractions of a degree. It looks like magic, but it's all engineering, and that's not all. Some spacecraft use something even cooler: reaction wheels. These spin inside the spacecraft and make it turn without firing any gas. It's like an invisible steering wheel floating in space. Super smooth, super efficient. But how does the rocket know it's pointing in the right direction? That's where star sensors come in. They look at the stars in the sky and compare them to a map stored inside the computer. The stars don't move, so they work like a cosmic GPS. The rocket can figure out exactly where it's facing just by reading the night sky. All of this is happening all the time, while it's flying, while it's orbiting, while it's maneuvering. The rocket is constantly adjusting, spinning, correcting, realigning. Because in space, even the tiniest mistake in direction can mean missing your target by thousands of kilometers. All right, the rocket made it to space. But does it have to keep its engines on the whole time? Does it need to keep burning fuel to stay in motion? The answer is no. And that's exactly what makes space so amazing. Here on Earth, everything needs constant force to stay moving. Cars, planes, even a skateboard. There's air, friction, gravity, all trying to slow things down. But in space, none of that exists. No air, no resistance, no wind to stop you. So when a rocket reaches the right speed, it can turn off its engines and just keep going. Forever. This is thanks to something called inertia. An object in motion in space stays in motion, unless something acts on it. The rocket fires its engines to accelerate, but once it hits the speed it needs, whether to reach orbit or head to another planet, it can simply shut everything off. And it'll keep gliding through the void, effortlessly. Here's a real example. The James Webb Space Telescope. It launched in 2021, boosted by a rocket out of Earth's orbit. After that, just a few small corrections using tiny thrusters. The rest of the 1.5 million kilometer journey? It coasted. That's how most space missions work. Rockets only fire during key moments, like liftoff, orbital insertion, specific maneuvers, or landing. The rest of the time, they're just coasting, silently saving every drop of fuel they can. Because in space, carrying fuel is expensive, really expensive. After completing its mission, the rocket, or rather, the capsule, needs to come back home. And this is one of the most critical moments of the entire journey. Re-entry into Earth's atmosphere. Out in space, it's all silence. But when the capsule starts descending, things change completely. The capsule enters the atmosphere at over 25,000 kilometers per hour. And at this moment, the air becomes a problem, literally. The friction with the atmosphere heats the capsule's surface to over 2,000 degrees Celsius, hot enough to melt steel. To survive this, the capsule uses a heat shield. It's a special layer that burns away in a controlled way, carrying the heat off and protecting everything inside. It works like a shield that slowly breaks down, saving what's behind it. Meanwhile, the capsule slows down with the help of air friction. From thousands of kilometers per hour, down to a few hundred. When it's slower and closer to the ground, the second phase kicks in. The parachutes. First, small ones open just to stabilize. Then, the big ones deploy, reducing the final speed to about 20 kilometers per hour. And then comes the final touch. Landing. Some capsules, like SpaceX's, use small thrusters to soften the impact. Others, like NASA's, splash down in the ocean, where rescue teams are waiting. From space back to Earth, the journey home is a challenge of engineering, heat, and timing. One miscalculation, and the capsule burns up, or misses the landing zone by thousands of kilometers. But when everything goes right, it lands softly. Mission accomplished. Thanks for watching. If you liked this video, make sure to subscribe. Hit the like button and share it with your friends. Leave a comment below telling us what you want to learn about next.